There we are.
Yeah.
Yeah.
It takes a while.
We are live.
Oh,
Yeah.
Anything
Yeah,
you
just
say
look at that.
can and will be recorded.
Yes.
it
Looks
is
like
live.
it's good.
Actually,
Yeah.
it is live.
Okay, I think we can start. So, very pleased to welcome Graham Cormode. He's going to be speaking to us today, and I will let you introduce. I could read your topic.
Yeah, that's fine.
I'll hand it over.
Thanks for coming along. We're a small enough crowd in the room that at any point feel free to interrupt, disagree, walk out, all of the above. So this is I guess work in progress with my student Tejas and my longtime collaborator Divesh from AT&T. So it's part of this ongoing program, linkage and anonymisation. This is very much on the anonymisation side, although obviously there are linkage questions lurking always. So it's always good to start with some horror stories. We're not that far past Halloween, indeed we're not that far past November the 8th. So I don't know how many of these are familiar to you. Do people know the New York taxi limousine story? A few nods. Okay, I'll do quick ones on each of these just to sort of refresh. So all of these stories are about well-intentioned people and groups who made decisions that they came to regret. And they're all around data release. The New York Taxi Limousine Commission had a huge amount of data on trips taken in New York taxis from, I think it was the year 2012, 2013, about a year's worth of data. And the kind of data that you get in there seems innocuous, right? It's things like when did the journey start and finish, where was the pickup point based on GPS, where was the drop-off, what was the fare. Not much more than that, right? Maybe a bit of information about tip and basically that, whether someone paid by cash or credit card. So it's one of these things where you think, well, there can't be much of a privacy concern to begin with, but nevertheless they took some steps. So what they tried to anonymise, because in this data you don't even know who's in the cab in that data set. The only identifying information in that data set was information about the taxi itself. It's sort of each taxi in New York has a unique license, sort of 4-digit alphanumeric code. So what they did is they masked that information, but they did it in a sort of consistent way so that the same cab in different places in the data set would have the same sort of novel identifier. And to cut a long story short, the mistake that they made was that anonymisation was easily reversible. So the function that they used to take the cab identifier and turn it into a supposedly masked one was not that difficult to reverse engineer. Okay, so I said it doesn't seem like the data is that sensitive, so what's the big deal? So the big deal is there's still lots of stuff you can do with that and linkage. So one of the linkages you can do is you can look for things in the public domain of people getting into taxis. So a good source of that is paparazzi photos of celebrities. So you see them, at a premiere, at a public restaurant getting into the taxi with a timestamp and a GPS embedded into the photo, link that with this data set, look up, find exactly the record, because they put all the records in, and see where they went to. Okay, that's probably not ideal. And you can do other things. So another thing you could do in this data was find trips associated with relatively specific locations. Right? So GPS is not perfect for telling exactly where someone is, but there are some locations in New York that are relatively remote. So the example used was an adult entertainment venue, where again people going there might not wish their visits there to be a matter of public record, easily searchable. And again, you could sort of find people that were picked up at this location at 2 in the morning, and you could see pretty much exactly where the taxi dropped them off back at home. Okay, so that's one example where people tried to do anonymisation and it was generally seen to be problematic. Commonwealth of Massachusetts Group Insurance Commission released a lot of health record data where they masked out the identifying information but left enough partially identifying information like exact date of birth, the postal area and the sex of the individual that you can do a pretty good job of linking back to that. Find your friends and neighbours' health records. Netflix in their celebrated competition when they released lots of data about people's viewing habits, they did some mild perturbation to that data, but not enough that you couldn't go and find an open source where people had publicly admitted that they'd watched a subset of those films, be pretty confident in your linkage, and then find out what's the subset of films that they've watched on Netflix that they haven't admitted to in public. And again, you know, interesting things about revealing people's preferences and beliefs through that. AOL putting out lots of data about searches that people have done, again, trying to mask who made the search. In fact, they don't even necessarily know who made the search, but making it linkable through the data set so you can see a complete list of searches that someone has done, and enough people consistently search for their own name and their own address that you can then, you know, pick those out reasonably easily and see what else they've looked for. NHScare.data, we're going to do something quite similar to the Massachusetts effort. That was sort of stamped on after an outcry a few years ago. There was a moratorium. It seemed like that effort was dead, and so all that happened is then private companies like DeepMind decided that they would just make private agreements to access that data and promise to be good. Okay, so those are sort of the stories, those are the kicking off point for why data anonymization is not an easy problem. Right? My evidence for that claim is that enough people have tried thinking they could do it and got it wrong, that I think we can conclude it's not easy. And you know, this therefore has been a great incentive for lots of researchers, you know, from my discipline of computer science, from statistics and beyond, to try and come up with, you know, technical solutions to this problem. And so there's another great long history that I won't go into of about 15 or 20 years of attempts to come up with a technical solution, and then follow-up papers that point out relatively big problems with the proposals. But to kind of jump to sort of the starting point for the technical component of what I want to talk about today, I'm going to jump straight into differential privacy that I know people have been talking about a lot during this program, as you know, not something which claims to cure all ills, but which is more robust and perhaps just more precise about the claims that it makes for itself, so that we're on a little bit more stable ground when we think about using differential privacy as a mechanism for releasing information about data. So this is, you know, goes back just over 10 years now to work by Cynthia Dwork, Frank McSherry, Kobe Nissim, and Adam Smith. And the first thing to appreciate about differential privacy is it is not a recipe, it's not an algorithm, it's not a process. It's a property that a process might have. And it's a statistical property, so we have to think, you know, in my language, I say, you know, we talk about whether a randomized algorithm has this property, has this parameter epsilon, if, you know, this slightly opaque looking statement about probabilities holds, which when you sort of take it apart is really just saying that the chance that I see a particular output or property on an output when I run this random process on a particular fixed input should look pretty similar, that's how I'm interpreting this inequality, pretty similar to seeing the same property on outputs of the same random process run on a very similar looking input. So, so more intuitively what this is trying to say is that if I just slightly modify my input, if I include your information or I don't include your information, I can't really deduce anything about that difference easily just directly by looking at the output, because the probability of seeing those two things is the same. There's e to the power epsilon. You know, we're assuming epsilon is small, so this is saying this is a ratio pretty close to 1. Okay. So this is a nice definition to work with for a number of reasons. One, I guess, is that sort of in microcosm you can look at certain simple processes and directly reason about probabilities of seeing certain outputs given certain inputs. Right, for a simple enough procedure, you can almost by hand work through this. Of course, people want to do things that are more than just sort of simple procedures. We'll get on to that in a minute. So maybe sort of the first simple procedure that you might want to follow that would achieve this property is say, well, okay, so I want to release some statistic. Let's just say, the count of the number of individuals in my data that satisfy a certain criterion. The kind of thing people have been doing for years, because it seems like a reasonable thing to do, is to say, well, take that true count on my data, draw from a reasonable looking distribution, draw some noise, add that noise on. Differential privacy sort of says, well, if you choose your noise distribution appropriately, particularly if you choose the scale and the shape of it appropriately, then you can meet this kind of definition. So if you accept that this is a definition that you want your process to meet, then you can meet it by noise addition. And really what this tells you is this is sort of the scale of the noise that you need to add. You need to add noise of a sufficient scale to effectively hide the presence of an individual. It introduces sufficient uncertainty that you don't know whether or not someone's information is included in what's reported back. Okay, so sort of more formally that turns into a slightly more general process that says for some function that you want to reveal about your data, call that function f, you can sort of calibrate the scale of the noise that you need to add by computing what's often called sensitivity. So that's, some people like to say lipschitz, but it's basically you're just looking over all similar inputs, so two feasible inputs to your function that differ based on the contribution that one individual can make. Just look at what's the maximum change in the output of that function, and that gives you essentially the scale of the noise that you need to add. So something as simple as just counting up how many people within a particular group satisfy a certain property, then the sensitivity of that is just 1, because if I add or remove one person, then that count changes by at most 1. And then that plugs into what's the shape of the noise. People are probably quite familiar with the Laplace distribution, this sort of symmetrical exponential distribution centered around 0. You add noise whose parameter depends on both this scale S and also that parameter epsilon that sort of determines the ratio of probabilities. If you don't like continuous things, you can look at the discrete case, and the discrete analog is the symmetrical geometric distribution. So that gets you sort of first steps into this. You might be thinking, well, if I want to do something that's a little bit more computationally complex, I don't just want to report simple statistics on my data, I want to do all kinds of clever clustering or fit some kind of machine learning model to my data. I'm going to need something a bit more just than sums and counts. There's also what I think of as the glue that says, well, you can start thinking now about sort of individual steps, individual pieces of information that you can release about the data. And I can then think about, well, what's the composition of those? So, my hypothetical clustering algorithm might look at lots of statistics of the data simultaneously. Well, you have these nice composition rules that basically say, in the most common case, if I sort of take one output O1 that meets an epsilon 1 privacy, another one O2 that meets epsilon 2 privacy, then you just do the simple procedure of adding up the epsilons, right? So you can kind of reason in a fairly modular way about the overall privacy properties. If you do a lot of that, then you realize that this epsilon parameter that you're trying to sort of keep moderately small starts ballooning quite quickly. So a lot of the sort of the algorithmic thought around these ideas is to say, well, how do you start to think of epsilon as a parameter that you want to sort of work within? We often talk about a privacy budget. We have some target epsilon that we want our whole process to meet a guarantee relative to, and we're then trying to slice that up to say, okay, this part of the algorithm is going to have this much of the budget, that part of the algorithm is going to have that much. Where we can be a little bit more relaxed is if O1 is sort of looking at one subset of people, and O2 is looking at a subset which is guaranteed to be disjoint, then you no longer add, you just take the max. So that's a useful sort of technique for sort of slicing up if you can kind of partition your data into different pieces and do different parts of the work on different pieces. So, this is sort of my quick intro to sort of differential privacy. The number of pieces, I mentioned these sort of approaches, what we call mechanisms, based on adding either geometric or Laplacian noise when we're looking at a function of the data that's numeric. Not everything you want to do is numeric, so you might want to look at other kinds of other functions where your output may be drawn from a set. So there's other mechanisms that let you work on that. And from these and other sort of primitives, a whole sort of zoo of algorithms has been defined to give differentially private outputs for different functions. So those are your primitives. Then you've got this sort of glue or cement to put them together, and you can sort of go off and with this toolkit and start coming up with here's my differentially private clustering algorithm, here's my differentially private classification algorithm for this particular classification model, and so on. And that sparked an entire industry within computer science and beyond. And there are some other sort of useful facts to remember. Things like if I give you some output which is differentially private and I don't give you any further access to the input, whatever post-processing you can do, whatever inference you might put on that, doesn't change those privacy properties. And that's another way it can help you think about algorithmic design, because you think, what are the parts of the algorithm where I really need to get my hands dirty with the data, and what are the parts where I've kind of pulled out the information that I need and it's now just kind of playing around with it. Then I'm no longer having to reason about privacy budget. Okay. So what are sort of the limitations of this approach as I've specified so far? So one is just to be absolutely clear, it's not, an algorithm is not a solution, it's a property that a process might have. So you can have differentially private algorithms that do a really good job of answering a particular question, and you introduce the minimum amount of noise that you need to get as accurate an answer as you possibly can. And I can give you no shortage of not particularly good differentially private algorithms. So the best differentially private algorithm is the one that reads in the data and then just outputs null. Right? Perfectly meets the definition and with certainty reveals no possible information about the individuals, but obviously doesn't really tell you anything of interest either. So it doesn't guarantee you that what you get out is useful. And if you just sort of blindly use the kind of primitives that are available, you're not necessarily going to get anything that gives you any great insight into the data. Another issue that I think comes up when we talk about anonymization. Often we talk about anonymization, we have this idea that data comes in a particular format, and this sort of perturbation, transformation, scrubbing goes on, and what you get out sort of looks like what you put in, but doesn't, somehow magically doesn't reveal anything about any individual. Well, I mean, the way that differential privacy is defined, it almost precludes that. Not entirely, but you're going to have to kind of work hard in order to get output that sort of meets the same kind of structure and format as the input data, because any sort of individual, let's assume that my data is a nice table of records, each row is information about one individual. What the differential privacy guarantee almost immediately tells me is I can't sort of have something that operates a row at a time and outputs something that's sort of a function of an individual row, because if I do that, then I've got to add noise sufficient to mask out the contribution of that individual. So it looks like I'll just get noise out of the end. So what you'd like to do, you've got this sort of picture in your head. You've got some raw data. You want to feed it into the analysis, and oh well, I suppose I better do some anonymisation. So all right, what do? I kind of first feed this into some algorithm that meets this nice differentially private guarantee, and then I get something out that probably looks more like statistics about the data than the raw data. And then I try and feed those into the analysis, and I've got to rethink, well, what's my analysis going to look like? Because the analysis that fed off the raw data is going to need some tuning to be able to feed off the statistics and the representation that I've built. And sort of what I've assumed all along is that we have this raw data, that someone has carefully collected this and it's held in some location by someone who's moderately trusted to sort of aggregate and run this differentially private algorithm. And that fits some scenarios, but it doesn't fit others. So what I'm going to talk about today are sort of some relatively recent work that sort of looks at this assumption and maybe also looks at this property a little bit and sees what else we can do here. So this assumption that you have a third-party aggregator, what if I don't want to trust someone to collect all the data? If you're a cryptographer, then your eyes light up because this gives you the opportunity to pull out all kinds of arcane, homomorphic, cryptographic, circuit garbling kind of technologies that let people, and secure multi-party computation, that let people collaborate based on encrypting their data and combining it in some clever way so that you end up with the encryption of a function of the combination. Good for them. That's not what I'm going to be talking about today. This idea of local differential privacy, it's sort of come to the fore over the last few years from a number of places. Does what I said a few minutes ago would be something that you think you wouldn't want to do. Defines a differentially private process that everyone runs separately on their own piece of data, and then they provide their garbled output to a central aggregator who's no longer as trusted because that aggregator is not seeing the true raw data, they're seeing some masked version of the data. And when I first thought about this, I thought, well, based on my previous understanding of differential privacy, that just sounds wrong because you've got to introduce noise. And ultimately, the reason that you've got any hope of doing something here is almost a statement about variance. It's a statement about that if you look at sort of what might happen in a simple case, you're going to add up all these results, which you can think of as signal plus noise. So you get the true sum of the signal plus the sum of the noise. You can think of that sum of noise in terms of maybe sum of variances and see that those variances will sort of grow linearly, but in terms of what that means about a sort of a deviation around the true answer, you can kind of see actually, yeah, maybe it's not going to be so bad. And that's basically what we'll sort of look at right now. And this is one of the interesting things. It's interesting to me because for all this talk about anonymisation and the motivations for doing it, the fact we've got all this data that we want to release, this is one of the few examples that's sort of being done wholesale. So if you have an iPhone on the latest operating system, if you have Google's Chrome browser, then built into that is some technology that does this. That's collecting some relatively simple statistics about activities, or at least has the potential to if it's enabled, and then can ship that back to the relevant company so that they can sort of learn the kind of things that people are doing with a nice sort of privacy statement hidden in the boilerplate text that says this is done with respect to your privacy and carefully and under this great differential privacy stuff. So you might then be wondering, okay, so what is this groundbreaking new algorithm that all these cutting-edge technology companies have implemented in their latest browser and operating system? It's something that has about 50 years of history. Technique, I think, familiar to many people under the name of randomized response. Right. So we're going to exactly what that is on the next slide, but I don't know what this says about innovation, that you know, people sometimes say, oh, you know, you come up with a great idea and you wait 10 years and maybe some people start to use it. Well, I'd say this is about 5 decades. But it's also that, you know, this is kind of a revitalization of a topic that, just talking to Chris beforehand, he was saying it seems a bit of a dead end previously, but it's had a new lease of life, and there's new questions to ask about this. Getting you into lots of questions about, so this is being used to generate relatively simple counts, and you can start to think about what other kinds of things can this idea of local differential privacy let you compute. Okay, so I think I'm supposed to give a trigger warning. This slide is going to include the word election, and it may even refer implicitly to opinion polling. So randomized response, as I sort of think of it, is something that was designed for surveys when you're dealing with a sensitive question. Right? So maybe that sensitive question was, how do you intend to vote in an upcoming election? And people don't want to necessarily admit to their chosen candidate. So you have a question, let's assume it's a binary question, there's 2 possibilities, but you're not confident that people will respond honestly. Okay, so this idea from the 60s was, well, if people are going to lie anyway, let's tell them to lie, but try and control exactly how they choose to lie. Right? So what that means is you get out your trusty biased coin. This is one variant, but I think it's fairly representative. Toss your biased coin. So you'll give the biased coin to the respondent, turn your back. They toss the biased coin, and if the biased coin comes up heads, their response is their true response, and if it comes up tails, their response is the opposite of their response. So assuming you can invest the hours necessary to explain to an ordinary member of the public how this works and why it protects their privacy, then this is an effective way of gathering information, because what you get, you know, as you sort of look at a large enough population, right, we've got this probability P that's telling you what's the probability you're getting the true response. You've got some unknown parameter phi, which is what you're trying to estimate. Then you can just pretty much write down what you expect to get in terms of the number of people that say yes or answer, you know, a particular output under this process. You get sort of the probability that they're told to tell the truth times the unknown parameter scaled up by the population size, plus all the people that are told to lie and have the opposite answer. And that's just an equation. So you can kind of work out sort of an unbiased estimator for the unknown population parameter phi, just by sort of seeing what result do you get and plugging in the known values of P and N. Okay. The sort of the caveat to that is, of course, this is really hard to put into practice because people don't understand this or find it difficult to sort of trust this. You know, again, we're saying beforehand, maybe they just sort of suspect that there's some trick going on and that their true answer is somehow being extracted from them. Okay, so that's the basic, and kind of this, how does this connect to differential privacy? It's kind of almost a one-line observation that, you know, this is an algorithm over 2 possible inputs and 2 possible outputs, and so you can take that definition of differential privacy and just say, well, that's going to hold if I can reason about the ratio of seeing the same output for the 2 possible inputs, and that ratio is just P divided by 1 minus P. So in almost a trivial sense, this you can just plug this into the definition and say this meets differential privacy with this parameter. EC epsilon is P over 1 minus P. So what does this parameter mean? Well, obviously, if P is pretty close to 1, then what you're getting is just people telling you the truth most of the time, and there's just a tiny bit of noise. And so you might think you don't get much privacy, because if you see someone that says yes, then you're much more likely to believe that they truly mean yes rather than they were asked to lie and say yes. So you get less privacy for a larger P. But conversely, you could sort of look at the variance of this and say, obviously, you're going to get a lot of variance. But it fits into this model of local privacy, that someone is effectively running an algorithm locally on their true data and revealing only perturbed data. And that's sort of the essence of what Google and Apple are up to in collecting statistics about, you know, have you been to a particular website or not, or, you know, do you fit into a particular category or not for using an app, this kind of thing.
Well, except that, you know, they're doing it and aggregating it.
Well, yeah, so what I haven't talked about here is the aggregation, right? So obviously when, a little bit, but you know, when you aggregate this...
They're flipping the coin for you and then collecting as well.
Yes.
But I'm sure they put the appropriate...
I'm sure they
firewalls
have.
and so on in place.
Right, so there is...
So it's a bit...
Well, there's an interesting side issue here about, you know, so this doesn't seem to work if you actually give someone a coin. They're just going to get confused. If you give someone a device and you tell them it's doing something clever to protect their privacy, somehow either they're a little bit more persuaded or they were sufficiently indifferent to their privacy to begin with that they don't mind either way. So one possible argument is that this whole technology as it's currently deployed is more to give the aggregators protection against regulators to say, look how wonderfully well behaved we're being with this data. We're not actually seeing the true values of any individual person, we're only seeing these aggregated noisy versions.
So different people couldn't set different keys. Was there extensions which allows that?
People have looked at that. I mean, it's quite natural for people to give different Ps, and if you then report back, you know, what is my noisy output and the P that I use to generate that, you can start, you know, writing, you know, long lists of equations and solving them. And that gets you into, yeah, sort of a notion of what's your privacy parameter. Yeah. All of that can be done. So what I've been looking at is what I think of as sort of small group privacy. So this is where instead of looking at one individual, or instead of looking at all individuals, you say let's just get a moderately small group of people who are prepared to locally aggregate their data and then run some anonymization, some masking process on that data. Right, you know, so the canonical thing would be, you know, it's a family who sort of share a house and share a internet connection, or, you know, an office setting, or, you know, through the aegis of a social network, something like that. So we have some small group that have enough mutual trust to pool their data within them, and then want to kind of wrap some privacy around that. So this is sort of just playing around, sort of teasing around with this definition of local differential privacy, where we want to think about what happens when you get this group. Can you maybe get a little bit more accuracy because we're sort of working not with sort of single bits but with sort of small integers, and get, you know, maybe slightly improved results. So the local the randomized response is a fairly simple process to define. You could define it as I did back here, you know, in terms of procedure. You could also just write down essentially, you know, the probabilities that say, you know, if my input is this, then what's the probability distribution of my outputs, right? And that's how we're going to be thinking here, right? We're thinking about basically saying we're going to describe a process entirely in terms of its, you know, essentially a set of probabilities that define the output distribution given the input. So for each possible input, you've got a distribution. So now we're sort of set up those parameters. We're now starting to think about how, you know, what is our process here? Well, we're sort of in the realm of design in a sort of numerical sense. We're trying to design these matrices of probabilities. So we might want to think about what are we trying to optimize here. So I'm going to talk about sort of the simplest case, the simplest generalization of randomized response, which is you've now got a group of n different people. They each have a bit, a 0 or a 1, we want to facilitate release information about the sum of those bits. You know, how many people have a 1 bit. So we're going to look at cases where the input effectively we've aggregated. So the input is some integer in the range 0 to n. The output will constrain that to be the same range. Then what we're basically looking at is defining what are all these conditional probabilities, the probability of seeing an output I given that the input was j. Differential privacy then plugs right in here and says there basically must be some ratio between, now this notion of a neighbouring input is just j and j plus 1. Kind of simplify things a little bit there. So think of this as alpha as capturing that e to the epsilon. You've got some bounded ratio alpha between neighbouring entries, whichever way around they happen to be. Okay, so that's just a constraint that my probabilities have to obey. What I might want to look into optimizing would be to say, I guess I can just start to think of this as a kind of sort of mathematical design kind of problem. So I might think about a loss function. Right, so let me kind of threw this in out of nowhere. Let me say where this comes from. So what I'm going to look at is sort of the total loss, the probability that I see a particular output given an input, times some function that is penalizing how far away the output and the input are. Right, so one way of doing that is just to say, look at the difference and take that to some power p. So then I can think of this as, I want to look at a weighted sum of this loss function. So I might want to think about these weights, wj's, as sort of a prior that says, given my prior belief that the input was j, that's how much I'm going to weigh the loss of telling you an I instead of the true answer j. And then there's this little cheat at the end here where I'm scaling by sort of 1 plus 1 over n, which is basically that when we computed this on some examples, this was a nice correction that sort of made the simplest possible mechanism have a score of 1. So we're trying to beat a score of 1, whatever n happens to be. Okay. And to further simplify things, we're just going to treat these weights as uniform, and we're actually just going to look at the 0th power here. So we're just really going to look at the sum of the off-diagonal probabilities. We're trying to minimize the probability that we give you any wrong answer. You can plug in other functions here and follow down where that path leads you. But this path took us to some interesting places, we thought. Okay. So what that says is basically we have some constraints and we have an objective function. Okay. So we started looking at that, we sort of played around with those and we realized that we actually wanted more structure. So sometimes you want your mechanisms to obey structure. And the reason was we sort of found mechanisms that seemed to optimize this kind of objective, and they looked weird. They did kind of weird things we thought were undesirable, like putting lots of probability mass at extreme values. So we said, well, let's look at some of the additional constraints you might want your mechanism to have. Okay, so I'm afraid these are a little bit unintuitive. I'll try and give a quick intuition for each one. So you can think of this mechanism that we're designing, and essentially is a matrix of probabilities. So you can look at properties that sort of run along the rows of that mechanism, and you look at properties that run along the columns of that mechanism. So you might want to say that a reasonable thing, given we're trying to maximize the probability of giving the true response, is to say, well, this true response should be more likely than seeing the same response for any other possible input. So if I see an I, then sort of with the uniform prior, it's sort of a maximum likelihood that was actually what the input was. More generally, you might want to say, well, rather than just having this sort of diagonal element be a peak, then you might want sort of a nice monotonicity that says as you get further away from the true answer along a row, then your probability decreases. It's just the kind of things that you'd naturally come up with. So you can look at these kind of things along a row and say, your diagonal entry in a row has to be the maximum along that row. You can ask the same things along the column. So you can say, is the diagonal entry the maximal value in its column. So that's saying that given a particular input, J, the most likely output for that input should be the true value itself. Another property that you may or may not want is one that says, well, if we're so concerned with these diagonal values that are basically the probability that your mechanism reports back the input it was given, perhaps you want to make them all the same. Perhaps you want sort of the probability that your mechanism reports the true answer to be the same whatever the input was. Not necessarily obvious that you want this, but it's a property you can look at how costly is it in terms of this objective function, is it to add that constraint? Another thing you might say is, so the most trivial mechanism I can come up with here is sort of the useless one that takes the input, ignores it, and just uniformly picks one of the permitted output values. Right? So we'd better be sure that whatever we do, we're doing something that's slightly better than that. So we'll call that the uniform mechanism, where the probability, well, all the probabilities are just the uniform probability. So this property of weak honesty says, are we reporting the true answer with probability more than uniform yesing? Again, it's not. You could just about think there might be a case where you might not want to have that property, right? Because maybe because of some of the constraints you have, you might want to compromise that for a few possible inputs so that you can increase the sort of the honesty probability of other inputs. But again, it's not an unreasonable property to have, so we're going to look at what's the cost here of including that. And the last one is sort of a symmetry property that says, if I think about my situation, I've got some natural symmetry here, right? That because my cost function just looks at how far away I am from the true answer, I'm working within this bounded range, sort of 0 to n. Sort of the natural symmetry property is this sort of mirror symmetry along the off diagonal of the matrix. Right? It neatens up your mechanisms, and it turns out that you can always achieve that. So whatever combination of properties I ask for, if I ask for an optimal mechanism that has a particular combination of properties, I can give you, based on that, a symmetric mechanism that meets the symmetry criterion that has the exact same objective function. It's going to be sort of an argument around kind of mirroring a non-symmetrical one and averaging and arguing that the cost ends up the same. Okay. So we ended up taking symmetry off the table with, what is it, 1, 2, 3, 4, 5, 6 or 7 different properties that you might ask for. An objective, which is to try and optimize a particular kind of loss function, and to see what kind of things you come up with. So the first thing you realize is that if you look at how you would write down all these different properties and all the constraints and the objectives, they're all linear. They're all linear functions. Right? The objective function ultimately is actually just linear in the variables, which are these probabilities. All those properties I just listed individually can be expressed as a linear constraint on the probabilities. And the differential privacy, which asks for bounded ratios, is effectively a linear constraint on the probabilities. So, this is great news, because it means rather than do anything particularly difficult, we can just write down a linear program and solve it. So if you say, right, I want to find an optimum mechanism for a particular n that meets differential privacy, is symmetric, and has one of those other properties, let's say fairness, just encode all of those constraints as linear constraints, plug them into an off-the-shelf solver, and I'll get something out which I'm convinced is optimal in terms of that particular objective function. So we did that. We did that for a while. We sort of played around, and what we found interesting was, even though there's 6 or 7 different properties you can ask for, so there's 2 to the 6, 64, or 128, different possibilities, we only saw about 3 different behaviours. Like, aha, something is going on here, we can understand this a bit better, there's some structure. And indeed, you don't necessarily always want to have to go off and solve a linear program. It's straightforward to do, but it's kind of time consuming, and if you want insight into what are the mathematical objects that you're designing here, then it would be nice to have explicit constructions where I can say, no, this entry is exactly this value, and then I can sort of understand, analyze and see why they have those particular properties. Okay, so let's start sort of with the least restricted case. So we looked at saying we want differential privacy, optimize this objective function, don't ask for any more properties. And what came out had symmetry without us asking for it, and it had that property of being row monotone. And it looked like this. Right? It's very, very structured. So what is it? You've got elements on the diagonal that are mostly the same except for the corner elements. And the differential privacy property says that you've got to have this ratio at most alpha between row-wise neighbours, and you meet that property exactly. So your corner element is x, then its neighbour is x times alpha, x alpha squared, and so on. For these, the diagonal element is y, and as you move away, you just increase powers of alpha. Right. And x and y also have nice expressions in terms of alpha. So this was really interesting. We can't claim to be the first people that found this, because it turns out that this mechanism is actually quite well known from about 7 or 8 years ago. This is the truncated geometric mechanism. So this is what you get when you put, as we said before, a geometric distribution on your input. So your true input is this value here. You add noise drawn from a geometric distribution, and you get these nice decaying geometric probabilities until you hit the end. And then because you can't have -1, -2, -3, you just kind of take all that probability mass and dump it on the extreme value, either 0 or n. Right. And indeed, this paper sort of also used a linear programming approach to find this, or talked about how you could use linear programming to find mechanisms. So, okay, you can prove that this is the unique such optimal mechanism, and it has some properties, but it doesn't have all the properties that we came up with. Right. And it's not necessarily always desirable. So this was, I sort of mentioned earlier, you sometimes see these funny behaviours. So this is an example on small inputs. So n is 4. You've got 4 possible inputs, 4 possible outputs. And a relatively cautious privacy parameter of 0.9. So the ratio between any elements must be at most 0.9, whichever way around you place them. And what you see is sort of what I said, that actually all of the probability mass ends up on the extreme values. And your probability of seeing any output in the middle gets sort of squashed right down. And that feels undesirable, so you could start asking for some of these properties. You could ask for the fairness property that would even up these diagonals, or the weak honesty that would make the diagonal elements larger, and say, well, how much does that cost me to kind of get my mechanism to sort of be a bit more representative of the inputs? I mean, this is just doing what we asked it to do. It's minimizing that objective function, but it seems a little bit unsatisfying that the way to minimize the objective function is to just mostly give one of 2 possible answers. But the nice thing is, you can write down sort of almost just directly in closed form as a function of alpha, what is the score that it gets in terms of our objective function. Understand under what conditions does it have other properties. So what we looked at was these other properties. We had this fairness property that said your probability of giving the true response should be the same for all elements. And so this is something we found sort of, you can either write this down and then prove it, or you can just sort of find it by linear programming. This is something where there's not a unique solution to asking for fairness, but we kind of conjured this one up. It has a similar shape, right? So you've got all of your elements are y, which is your diagonal element, times some power of alpha. And initially you're sort of doing this thing where you're trying to have the maximum drop off, so you're trying to sort of maximally move away from y. But at some point you saturate, so rather than dropping this all the way down to, let's say, y times alpha to the 7 for this fixed example, you kind of saturate it here. And that's basically just because these are, because this is what do I want to say, column stochastic matrix, because the columns have to add up to 1. The easy way to do that is just to make sure every column has a permutation of the same set of values. So this is, I quite like the structure here. You know, it is symmetric, it is monotone along the rows, it's monotone up and down the columns, it has that fairness property, this base, and you can just kind of sort of solve the equations to figure out what is this y value, right? So you know exactly what are the values in the column, they've got to add up to 1, so that lets you solve for y. So basically this mechanism has all the properties that we've defined, has a nice explicit construction. Clearly you've got to pay for that, right? In terms of your objective function, you're going to pay for that because it's going to have a cost that's higher than, let's say, the geometric mechanism, which doesn't have that structure. And I'm going to sort of hand wave a little bit and say the cost is slightly higher. Right? So, and it's basically an n plus 1 over n factor higher, with a little bit of wiggle room, because the exact expression is a little bit ugly. So because this has all of the properties that we could define, because geometric mechanism has a few of the properties, it turns out there's just not much room within this design space. So this is sort of what we ended up coming up with. This is our sort of guide to the design space here. You know, do you want your mechanism to have fairness? Yep. Well, you might as well have the fair mechanism that we just defined, because it comes with every other property that you may or may not want for free. Otherwise, depending on this sort of issue, if this condition is true, then it means that the geometric mechanism has the weak honesty property, so you don't need to ask that question. So if your n is large enough, if you want some properties on the columns, if you don't care about the columns, then you're immediately working with the geometric mechanism. If you do want some column properties, and you want weak honesty, then you get what we call the weak mechanism, which is basically what you get when you solve the LP and you put that property of weak honesty into your requirements. So what we'd like to have got to was an understanding of the weak honesty property in an explicit form. What we end up doing is just saying, well, let's solve the LP for that. So there's more to do to try and say, is there some understanding of what happens under this sort of weak honesty property? This table may or may not clarify things. What it's trying to say is if you sort of look at all the different mechanisms we talked about, so we talked about the geometric mechanism, we talked about the trivial uniform mechanism that ignores the input and gives a uniform output, our explicit fair mechanism and the weak honest mechanism, then they all exhibit different combinations of properties. They have this uniform mechanism has the highest cost, this geometric mechanism has the lowest cost, and the other costs sit somewhere in between. Okay. So just to quickly wrap up in the last couple of minutes. So firstly, here's a picture to try and convince you that these things are indeed quite different. So this was my scenario where I put in alpha as 0.9 over a small input range, just so we can visualize this. So geometric mechanism is optimal in terms of the objective function, but basically pushes the probability mass to the smallest and largest outputs. The explicit fair mechanism achieves that equal diagonal value, and you can kind of see how the other values decay a bit from that. 0.9 alpha doesn't give you too much room to maneuver. And the weak mechanism is the one where we require that the diagonal value is greater than 1 over n plus 1, so that gives you a 0.2 minimum value there, but then it sort of compromises between these two, right? It pushes up a little bit on the extreme values, but not quite so extremely as GM. So you've got 3 different structures of matrices. Each of them are doing something optimal relative to a set of constraints, but we still want to know, well, are they any good? Do they give us something useful? And so I'm afraid these plots are a little bit small to see, but what they're trying, this is still sort of intrinsic evaluation. We're still looking at that objective function as we vary n, as we vary the size of the small group, right? So sort of way down at 1, all of these converge trivially into randomized response, right? If you just have one person there, everything's randomized response. As soon as you step away from that, the behaviors break apart. So this is sort of the trivial line. This is the line at 1 that corresponds to the uniform mechanism. This blue line is our explicit fair mechanism, which is more costly than geometric mechanism, but not as bad as uniform. Where things get interesting are in sort of cases like this, where the weak mechanism found by solving the LP, it starts off looking a lot like a fair mechanism, but as you increase the group size, essentially at this point, geometric mechanism, n is large enough that the geometric mechanism has the weak honesty property. So at this point they've converged. And in this case, with a very large privacy parameter, so a lot of privacy required, we never get a chance for that to happen. So here, the explicit fair mechanism and the weak honest mechanism basically stay the same until the group size gets really big, around 100. Okay, but what we actually want to do is say, well, what happens when we put some real data into this? So this is, it's just a small example. We took some real data, defined some groups within that data, and looked at a few different binary attributes for that group. So within each group we said how many people have at least 16 years of education, how many people in the group are female, how many people in the group have income above a threshold. So it's the same sort of colours here if you can see them, but red is our sort of cut-off point for trivial. Right? Red is just uniform guessing. So what we found interesting is as you kind of ramp up this privacy parameter towards 1, it's hard to do much better than guessing. Okay, that's reasonable. But that some mechanisms like, can't see the label very clearly, but this is a geometric mechanism, actually give you something that's worse than guessing on this particular input distribution. The intuition is that this version of geometric mechanism wasn't sort of trained based on a prior distribution that matched the behavior in the data. Whereas these other two, the dark one for the weak honest mechanism and the blue one, so let me say, sorry, we're measuring sort of a root mean squared error on per group outputs here. So smaller is better, and you can roughly interpret these numbers in an absolute sense of sort of how much better than trivial guessing are you doing. So actually it seems on this kind of data, when we're looking group by group, then these other mechanisms with a bit more structuring seem to be doing better for this different objective function. Okay. Right. So what we learned from that is, firstly it's fun to play around with mechanisms because you start off with good motivations and you end up playing around with equations and constraints and optimization. And what we think is, if working with small groups is of interest, then it repays you to put the effort into designing mechanisms specifically for those groups. We looked only at sort of the most basic question, which was just release the count of number of bits in a group. So you can immediately start saying, well, obviously I want to know about other statistics, other information about the group. What if my data, I think of not as numeric, but as graph structured data with connections, as trajectory data on movement. A question I don't even know how to say anything meaningful about is, most real data is multimedia, and we're so far away from even being able to sort of figure out what privacy means on there that it's a fun question to think about. And given that organisations are producing implementation standards for doing this, then maybe this is a suitable thing to sort of get agreement and standardisation on. And that's it. Thank you very much.
Thanks very much, Graham. So, questions?
If you go back one slide, one of the
Yes.
results kind of got quickly went down.
Yes.
Can you-
No, no. So this mechanism, it seems quite spiky, and it's So what we're showing here is as we change the privacy parameter alpha, what happens to this sort of squared error? I don't really know. It's unintuitive. The easy answer is to say, oh, it's just random variation. It doesn't look random enough to be random variation. So we've got to spend more time looking at that and trying to figure out what's going on.
Can I ask a general question? So this is locally. I may have missed your loss function, but globally you're aggregating or summing, are you, over these different groups?
To do this is focusing on looking at the sort of the loss per group for a different. So initially we looked at the loss per group just based on the loss function we defined, and this is sort of saying, well, what if we define the mechanisms based on one loss function but evaluate based on a different loss function, which is a little bit unfair. Maybe we should have also just tested them put this loss function in, but we're trying to sort of understand these the mechanisms as they've come out.
I'm trying to think in statistical terms, if you were interested in across the groups,
Yes.
whether traditionally in the randomized response might allow you to do
Yes.
some estimating mean across groups.
Exactly. So
sometimes
that is actually I didn't show the plots on that, but that is sort of the next step. And there, what happens is that the mechanisms are less distinct. So when you do the right kind of inference to sort of combine the outputs across all the groups, then they all do reasonably well. As n increases, you get a better and better estimate of that global behaviour.
In terms of getting the right answers.
But if for some parameters, sort of between group variation might be biased too
Yeah.
large or something.
Yeah,
by
exactly.
cutting this noise out the group level.
So we sort of here we've sort of spent a lot of time looking. You can almost think of this rather than think of this as sort of lots of groups. This is just using lots of groups to kind of look at the average effect per group.
This is quite related to some of the things we're thinking about which happens with contingency tables, where you have a perturbation matrix like this, but you often have this sort of turtlets. You often set zeros for points further away from the diagonal bands. So
we were trying to find these matrices. We sort of said these look like turtlets matrices, but they're not quite, because they don't quite cycle the way you want them to, right? Because it's not the same row cycled round, and it's not the same. It's almost the same column cycled round, but you're doing slightly different things.
Okay.
So we were trying to find out, was there a name for this, and we couldn't find it.
Okay, yeah, I probably missed that.
But it was interesting that sort of, I mean, this one was so the way this matrix comes out is sort of more explicitly designed. So what you're trying to do is you're trying to maximize this y, but the constraint is that you've got to have these ratios. You can have at most a certain ratio as you move away from the diagonal. So the most constrained column is sort of one that corresponds to a middle column, where you've gone as quickly down as you can here, and you've gone as quickly down as you can here, and likewise for every row. And that basically says these off-diagonal elements in the center row are the smallest they can be. And that then you have the constraint that it's stochastic, so it has to add to 1. And so it's the middle column that's constrained, and then it's like, well, what do I just need to do to make everything else add up? That's sort of the construction here. Whereas this one that comes out is, it's still a little bit magical to me that these things all add up to 1 on the columns. But yeah, there's various ways to kind of prove the optimality of this, but one way is to I think you do a few steps and you can kind of assume some of this structure, and then you can start looking column by column, and because the pairs of adjacent columns have almost the same set of entries, you can sort of do sort of Gaussian elimination by hand to just construct the entries of the matrix.
I can't remember the authors of the paper I'm looking at.
No. But if you had a series of zeros further,
If
from
you're
the
allowed to have
diagonal,
zeros
that
in
would-
these matrices,
that
yeah.
would breach some of your.
Yeah, so you're not allowed to have,
Constraints
under differential privacy, strictly enforced,
Oh, any zero.
you're not allowed to have any, well, you can have zeros, but what that means is just, you have these ratio constraints along the rows, so if you have a 0 anywhere, then that means the entire row is 0,
Right,
and that just means you've thrown away one of your outputs.
Right. Yeah.
So actually, yeah, being able to have 0 as, and not have an all 0 row would be a nice relaxation for us. And it might be allowable
Delta.
on the epsilon delta differential privacy.
Mm.
So we stuck to the epsilon
It
version.
fills up, you don't, use the delta to measure that.
All right.
Cool.
So thank you very much indeed,
Thanks.
Graham. For anybody who sent in a question, I apologise, but I will pass it on to feed the answer back hopefully later. So, right, thanks once more.